Let's discuss question number 44 from test sets. This is from thermodynamics. Ideal gas is flowing through an insulated pipe. So you have an insulated pipe where it's insulated. So Q is 0, can't go. It's insulated, and this is how the ideal gas goes. Now there is some friction, so obviously there will be a pressure drop. And what is asked is, in this process, what is the energy loss or the irreversibility rate? Now the irreversibility rate is T naught into delta S of the universe. This is how the irreversibility rate is defined. Now what is delta S of the universe? Now there is some ideal gas which enters, it has some entropy, so M1 S1 being the specific entropy, so I'm just multiplying with M mass, and out at the outlet it's, so mass is same, so ms1 is the inlet, ms2 is the outlet. Okay, now the change in entropy of the system. So how do you find out change in entropy of the universe? Now change in entropy of the universe is change in entropy of the system plus the change in entropy of the surroundings. Okay, the change in entropy of the system is what is entering it is, so let's calculate change in entropy of the system. So change in entropy of the system is what is entering it is positive, so ms1 is entering, ms2 is going out, so ms2 plus, so this is the increase in entropy of the system, plus there is some entropy generation. Okay, Sgen. Now delta S of the surrounding, so delta of the surrounding, you're adding ms2 to the surroundings and you're removing ms1 to the surrounding, so it is ms1. Okay, so if you add these two, so how do you calculate Sgen in this process? Now that is how it comes from TDS equation. Now TDS equation is something which is valid for all the process. So TDS is dH minus VdP. Let's apply this equation. This is one of the TDS equation. Now what is the change in enthalpy and what is this pressure change? Okay, now change in enthalpy, how do you find out change in enthalpy? Well, let's apply the first law. When you apply the first law, it's H1 V1 square by 2G plus GZ1, or Z1 is some heat added, is equal to final enthalpy, final velocity whole square, plus Z2 plus some work done. Now it's insulated process, Q is 0, there is no work done, velocities are all neglected, so H1 is equal to H2 in this process. So there is dH is 0, there is no change in enthalpy, so TDS can be written as minus VdP. So when enthalpy is constant, it's an ideal gas, so it's Cp dt, change in enthalpy, so its temperature is constant. So I can write this as minus VdP by T. It's ideal gas, so minus V by T can be written as, by using the ideal gas equation, PV is mRT, so V by T can be written as mR dP by P is the change in entropy. So now if I do it, the final change in entropy from inlet to outlet, so this will be minus mR ln P2 by P1. So that is delta S. Okay, that is delta S. So this is what is your Sgen. Okay, now if you add these two, delta S plus delta S surrounding, that is nothing but is Sgen, and that is nothing but the change in the entropy of the universe. So we need to multiply T naught, irreversibility rate is T naught delta S universe, that is nothing but T naught Sgen, and that is nothing but T naught into minus mR ln P2 by P1. Now pressure decreases, so P2 is less, so minus will go inside, which will make mR ln P1 by P2. So now it's just a matter of substitution. So T naught is 300 Kelvin, mass is 3 kg per second, R is universal resistance, so 0.287 kilojoules 10 power 3 ln P1, the initial pressure, there's a 10% drop, so the final pressure is 0.9 times P1, so it's 1 by 0.9. So this, if I calculate this, comes closer to 25.83 kilowatt. So this is the irreversibility rate, 25.83 kilowatt. The answer is B. Thank you.